Ready for a little science magic? Well, it's a trick so simple, yet so surprising. It makes you rethink how the world works. All you need are two small, identical balls. Hold one ball out in your right hand, hold the other ball in your left hand. Now, for the action. At the exact same moment, drop the ball from your right hand straight down. With your left hand, give the other ball a gentle push so it sails out horizontally. Now, listen and watch very closely. Which one do you think will hit the ground first? The one that dropped straight down, or the one that traveled a longer curved path? Many people guess the dropped ball will win. It seems logical. After all, it took the shortest path. But when you try it, something amazing happens. Clack. Both balls hit the ground at precisely the same time. Don't just take my word for it. Try it yourself. Stand up and do it right now. The sound of them landing together is the proof. This simple, stunning demonstration is the absolute heart of understanding something fantastic in physics called projectile motion. It's the science of anything that flies through the air, from a baseball to a water droplet. So, what is the secret behind this counterintuitive result? It's all thanks to a constant, invisible force you deal with every single day: gravity. The ball you dropped only had one motion to worry about: down. The ball you tossed forward actually had two motions happening at once. It was moving forward horizontally from your push, and it was moving downward vertically because of gravity. The key idea here is that these two movements are independent of each other. Think of it like this. The forward push you gave one ball didn't make gravity pull on it any slower or faster. Gravity just does its job, pulling the ball down from the height you released it. Since both balls started at the same height and were pulled down by the same force of gravity, they had to spend the exact same amount of time in the air. This principle of independent motions is the first and most important rule you need to know to become a master of projectile motion. It's a fundamental concept that explains so much about our moving world. Let's explore this idea a little further with another cool experiment you can do right at your kitchen table. For this one, you'll need a plastic cup. You'll also need a small object that fits inside it, like a marble, a grape, a tightly wadded piece of paper. Place the cup upside down right at the very edge of the table. Now, carefully balance your small ball on top of the upside-down cup. You are about to separate the horizontal motion from the vertical motion in a very clever and visual way. This demonstration helps us see the path an object takes. Get ready to act fast. With one quick, perfectly horizontal swipe, you are going to knock the cup out from under the ball. The goal is to move the cup so quickly that you don't push the ball forward or backward. Just a clean swipe sideways, parallel to the tabletop. What do you predict will happen to the ball? Will it fly forward with the cup? Will it drop straight down? This trick works because of inertia. Inertia is an object's tendency to keep doing what it's already doing. Before you swiped the cup, the ball was at rest. It had zero horizontal velocity. By whisking the cup away cleanly, you didn't give the ball any forward or sideways push. So, its horizontal motion remained zero. The only force that acted on it was gravity, which immediately began pulling it straight down. The ball was, in a sense, left behind by the cup, and gravity took over. This is a perfect example of an object with only vertical motion. Now let's change it slightly to see the full picture. Instead of balancing the ball on top, place the cup right side up at the edge of the table and put the ball inside it. This time, slide the cup and ball together along the edge of the table and then slide the cup right off the edge. As the cup falls, the ball falls with it, but they follow a beautiful curved path to the ground. This curved path is called a trajectory. The ball had horizontal speed from your slide, and gravity gave it vertical speed. The combination of the two creates that classic arc we see everywhere in sports and nature. We've seen what happens when you drop something straight down and when you launch it perfectly horizontally. But what about all the angles in between? Most of the time, when we throw or kick something, we launch it at an angle to the ground. To investigate this, let's build a simple piece of scientific equipment, a launch ramp. Prop one end up on a book to create a gentle slope. This ramp will let us launch a ball at the same speed every time. For your first test, set your ramp up at a low angle, maybe one thin book. Place a small, smooth ball at the top and let it roll. Don't push it, just release it. The ball will roll down, shoot off the end of the table, and land on the floor. Use a small piece of tape or a coin to mark exactly where it landed. That's its range. Repeat this launch a couple more times to check consistency. Now, it's time to change our variable. A variable is the one thing we change to see what happens. Here, our variable is the launch angle. Add another book under your ramp to make the angle steeper. Let the same ball roll from the same starting point. Where do you think it will land this time? Mark its new landing spot. Did it go farther than before or not as far? A steeper angle gives the ball more upward lift, keeping it in the air longer, but it might reduce forward speed. Keep experimenting. Try several different angles by adding more books. A very shallow angle might not give the ball enough airtime. A very steep angle might send the ball high up, but it won't travel very far forward before landing. Somewhere in the middle is a sweet spot, the optimal angle for maximum range. For many situations, this angle is close to 45 degrees. That's why athletes who throw or kick for distance, like javelin throwers and punters, aim near that 45-degree mark. Our eyes are amazing, but some things in science happen too fast for us to truly appreciate. To really break down the motion, we need a superpower, the ability to slow down time. Luckily, most modern phones have this superpower built right into their cameras. Using the slow-motion video function, you can reveal the hidden details of projectile motion. It's like having a science laboratory in your pocket. Let's start by recreating our very first experiment, but this time, we'll film it. Have a friend hold the camera or set it up on a stable surface. Start recording in slow motion, then perform the action. Drop one, throw the other. When you play the video back, watch the two balls frame by frame. You will be able to see with incredible clarity that as they move through the air, their vertical positions match up perfectly. At any given instant in time, they have fallen the exact same distance downward. Now, let's use slow motion to analyze the trajectory from an angled launch. At the very peak of its arc, the highest point it reaches, you can see something fascinating. For just an instant, the ball stops moving upward before it starts to fall back down. The best part about using slow motion video is that it allows you to see the two independent motions separately. Watch it once focusing only on the vertical, and again focusing on the nearly constant horizontal. As you become a scientist exploring the world of flying objects, it helps to know the right words. The first and most important word is gravity. Next up, velocity. Speed in a specific direction. Angle is the direction of the launch relative to the ground. The curved path a projectile follows is its trajectory. It's always a parabola. The total horizontal distance from launch to landing is the range. Put together, launch velocity and angle determine the trajectory, which determines the range, while gravity pulls the object down. Great science requires not just curiosity, but also a bit of care and precision. Be a good observer and keep things consistent. Do each test 3 times and record the average landing spot. Keep a simple lab notebook. Make a table, number of books, and distance the ball traveled. Be safe. Clear the landing zone, keep siblings and pets away, use soft balls, and test on a rug or grass when possible. Use common sense with your setup. 2-ball drop test. Use a low, stable surface, not a wobbly stool or a high ledge. When you throw, give a gentle toss forward. The goal is to observe physics, not to throw hard. Your mission: find the launch angle that gives you the greatest possible range. You have all the tools you need to solve it experimentally. Test 5 different launch angles. Define them by the number of books. 1, 2, 3, 4, 5. For each angle, launch 3 times from the same release point and measure the range. Calculate the average range for each angle. Which angle gave you the longest average range? Fine-tune your launch. Add books, remove books, or use a thin shim to zero in on the sweet spot. Record your attempts and share your results. Ask a question, test it, look at the evidence, and share what you've learned. Now go on, get launching.